Okay, sorry about that. Took a while to get it set up. Hello, everyone, again. My name is Sunil. For everyone who has seen me here last week, hello again. And for people who are coming in just for this week, nice to see you. So today I'll be talking about getting redshifts in the era of thousands of FRBs. So I just slightly tweaked the presentation. And for those of you who also attended the FRB 2025 conference, this might seem a little familiar. So apologies for the repetition from this year. I did try to include a little more in terms of content based off of the feedback that I got last time. So hopefully, at least some portion of it will be interesting to you. So without further ado, let's get started. We are in the era of hundreds of FRB host galaxies. That's for certain. For a long time, we have been ramping up our observations of FRBs or detections and also localizations. So CHIME is now capable of localizing with millisecond precision, something of the order of 200 FRBs every single year. So with this, you could do all sorts of really, really cool analyses, especially when you have an extremely bright FRB, which means your localization regions are truly 10 millisecond scales. So you can actually look at the individual host environment where the FRBs are coming from if the host galaxy is close enough. So all of this is great, but when you want to analyze a sample of FRBs and try to understand their host properties and whatnot, there are so many optical redshifts that you need to obtain. And being part of the F4 collaboration, whose main role in the last few years has been to follow up on FRBs and getting redshifts, this is no easy task. Getting 200 redshifts a year takes a lot of telescope time and a lot of effort from everyone involved. That's not to say that you can't do anything without FRB redshifts. There's a lot of analyses that you could do even without knowing where or how far away the FRB is. Case in point, two over here, Wu and McQuinn in 2023 presented this analysis where they looked at pairs of FRBs with intersecting nearby halos, and they were able to place constraints on the baryon distribution in these halos. Similarly, Lodrick Kahinga in the CHIME collaboration is working on a similar analysis, but this time only involving M31 because it's so big in the sky. So you have 30-degree radius essentially to play with. And so if you have a ton of intersections there, then you could probably try to say something about the gas inside the M31 halo. You could also do a cross-correlation analysis like Hao Chen Wang et al. Did in 2025, where they basically looked at the dispersion measures of CHIME Catalog 2 FRBs and correlated them with foreground galaxies in photometric redshift catalogs. And they were able to place constraints on the matter power spectrum, similar to the analysis that Kriti Sharma presented. But of course, life is better if you have host redshifts. There's a ton of analyses that you could do if you had them. Here are a couple of these examples. So you could try to figure out where scattering screens are for highly scattered FRBs, place constraints on the location of the turbulent screens with respect to the source and the observer. You could do all sorts of cosmological analyses where you try to correlate dispersion measure, extragalactic with redshift, and play various games like Flim Flam do, and also work by the DSA team to try to figuring out basically the matter distribution in the IGM and the CGM. And if you want to do any sort of like SED fitting or modeling, then it's good to have FRB redshifts. fitting for a redshift. Oh, sorry. As part of the SAD analysis can yield a lot of uncertainties in the measured or inferred galaxy properties. At the same time, if you wanted to look at the offsets of the FRBs within the host galaxies themselves, like Michelle Woodland and Alexander Mannings did, then you would also need distances to the FRB hosts. So you need redshifts. All of this to say, if you don't have redshifts, you could do science, of course, but it's much cooler to have redshifts. And shout out to, I guess, well, shameless plug to our team, F4, who have been leading this sort of optical analysis work for the last several years, basically since the beginning of my PhD. So it's been wonderful working with these people. And doing all sorts of optical analyses of FRB hosts. So what goes into measuring redshifts? First of all, of course, you need to identify which host galaxy it is and what do you need a redshift for. And to do this, you need path analyses. So basically a Bayesian method to associate FRBs with their host galaxies. The requirement for this, of course, is that you have deep enough imaging at the FRB location. And deep enough varies by FRB and by field. So here's a classic case of FRB 180924, the first localized one-off FRB. And you see this host galaxy right over there, sitting smack dab at the FRB location. So even by eye, you could say over here that there's no doubt that this is the host, but sometimes things are not as clear cut. Things are ambiguous, and sometimes the hosts are truly faint. So in case the FRB landed over there, that chances are that this object is something like a 25th or 26th magnitude source, and you really needed bespoke imaging to even see that object, as Apurva was mentioning previously. And here is an example of the case, basically what Apurva showed previously. And you sometimes need JWST imaging before you can even get redshifts. And that can be super expensive because it's not just getting JWST imaging, it's also convincing the JWST TAC that you need JWST imaging. And what that means is that you have spent a bunch of 10-meter class telescope time showing that there's nothing there, and you need to go deeper before you can actually use a space telescope and get this sort of association. And sometimes if you have deep enough imaging, faint sources will show up, and you could actually see that the host association changes as a function of their imaging depth. So if you have a shallow image, then you might consider something to be the host, but your path posteriors will update once you have deeper imaging, as shown here in this case by Dante Hewitt. So there are a couple of future imaging surveys that are planned. Obviously, LSST is in everyone's mind over here, I hope, and if not, please do keep it in your mind. There's also Euclid. Both of these surveys will be producing deep imaging catalogs, or deep imaging for large swaths of the sky. LSST will be mostly in the southern hemisphere, but Euclid will cover almost all sky. And especially in its visible band, which is pretty wide band, and it's practically only good for detecting a source, you can get down to 26th magnitude for entire portions of the sky that are outside the Milky Way plane within 6 years. And of course, LSST will be delivering 27th magnitude depth R band in 10 years. So these will be enormously useful repositories for identifying host galaxies in upcoming surveys, FRB surveys. So in case at the moment you don't have imaging for your host and you need to obtain them, here's how you go about doing it. First, you have to check the catalogs that I talked about last week. So there are several public catalogs, PS1, Pan-STARRS and Legacy Survey. They cover large portions of the sky, and reliably you can find hosts within, let's say, magnitude 23.5, 24 sometimes, especially if you look at some of the deeper parts of the Legacy Survey. If you need anything deeper, then you could get down to 25th magnitude with something like an hour or two of imaging with 4-meter class telescopes. And for the same amount of time with the 10-meter class telescope, like the Keck, you can get down to 27th magnitude. And of course, if you want to go even deeper, then you better be looking into space. JWST is your instrument of choice here. But the whole point of this talk is to see if we can get redshifts. And so one of the points that was brought up in FRB 2025 was, well, we could just use photometric redshifts. Why do we need spec-Zs for any of these? Let's say you have a robust enough host association. Why not just rely on these photometric catalogs to get photo-Zs? And yeah, there is some merit in this argument. Of course, there are many more sources which will have photometric redshifts than spec-Zs. And it's just, well, more often than not, as soon as you have an imaging catalog generated, as a immediate consequence, people will be creating value-added catalogs, and photo-Zs will be one of the first few products to come out of these things. And so here is an example from the Rubin Observatory's data release, and you could see photo-Zs are, they're kind of well behaved for the most part. If you compare them against spectroscopic redshifts. The issues, of course, with using photo-Zs is that you have to worry about accuracy and also some precision. So most photo-Z estimates are good to something like 0.03 times 1 plus redshift. It could be slightly better or worse, but that's the order of magnitude. But more importantly, you have to worry about these catastrophic outliers. So some of these extremely high redshift sources will get tagged as very low redshift by the photo-Z pipelines that people use. So these are two different pipelines. You can see how they behave differently, but this one seems to have a little more of these catastrophic outliers than this. But nevertheless, there will be always these sources. Also, something to worry about is at higher redshifts, photo-Zs are not going to be as good or not complete, I guess. This is simply because the photometry for higher redshift sources becomes harder to measure because they generally tend to get much fainter. And so it's a real problem if people here are considering really, really distant FRB's hosts. And this will be a thing in the era of DSA 2000. And in fact, CHIME already has, DSA 110, CHIME, CRAFT, all of these surveys will already have samples of unseen host FRBs that are just waiting to get JWST time for identifying hosts even. So, of course, it's valuable to assess whether we can do a good enough job with photo-Zs. And so to do this, I did a very simple exercise. I took this DMZ relationship from Clancy James's GitHub repository. So basically, this is my two-dimensional distribution for FRB DMs as a function of redshift. So I generated a mock catalog, and that's what, the blue points, that's what they look like. And I tried to simulate a sort of a very simple cosmological experiment. Of course, I'm not doing anything fancy. All I want to do is bin these FRBs by redshift and measure the mean value and the standard deviation. That's it. This can seem rather naive, but most complicated analyses basically use the McCart relation and the scatter in the McCart relation, as Kriti mentioned earlier. And this is one way to check if we are actually getting these measurements accurately when compared against spectroscopic redshift measurements. So what I did after that, of course, was went back to those mock FRBs and degraded their redshift estimates. So I added for the first part, I added a Gaussian uncertainty of the order of 0.03 times 1 plus z. And I asked the question, how do the mean value of the DM cosmic and the standard deviation change as a function of redshift bins? So this is a messy plot, but bear with me. The blue curves are produced when you have 1,000 FRBs. So if you just take a look at it, there seems to be a lot of scatter, but that's simply because of small number statistics, I guess. And these 1,000 FRBs span a large redshift range from all the way from 0 to 4 based off of the distribution that I was working with. So each individual bin might not have as many FRBs. So you're seeing a scatter of something like 10% around the mean value. So if I just compare Z-Fort DM estimates versus Z-Spec, ideally I would expect everything to be close to 1. But of course, if you have small numbers, you have some scatter. Of course, and you can see this effect as you increase the number of FRBs, the scatter gets smaller and smaller, and there's basically no bias. So if you have Gaussian errors, you can, and if you have large enough numbers of FRBs, you could do quite well with measuring the mean DM for FRBs. Same goes with standard deviation, of course, but there is like much more scatter here. Here we're talking about 25% scatter, or like sometimes even higher, depending on your redshift range, but typically order of like 25%. And of course, it also gets better if you have many more FRBs to work with. But like I mentioned previously, errors are not Gaussian, and in fact, the catastrophic failures are what really throw a wrench in the works, so as to speak. So here is an example of a simulation where I took 15 to 20%, in this case, 20% of high redshift sources. I defined this as anything beyond redshift 0.8, and I subtracted 0.5 from the actual redshift for them, so as to simulate a catastrophic failure. So these are high redshift sources that have been marked as very low redshift. And you can see this effect in the mean value estimate that you get. So as you would expect, the mean value at low redshifts becomes higher because now you have a bunch of high redshift FRBs that also have high dispersion measures, and so they're biasing up this redshift estimate. And even when you have hundreds of thousands of FRBs, you will still see a 10% effect in this case. Of course, it's a contrived example, but this could be the case if you rely entirely on photoz's. With the standard deviation, you could see that it's slightly better behaved, but even so, it's like consistently you see an increased scatter of the order of like 10%. So catastrophic failure is something that you have to really worry about if you're going to rely on photoz's. Could you use photoz's for foreground analysis? So if you want to say figure out which objects are in the foreground. I did some work looking into this previously, and here is a plot from my 2021 paper where I looked at this particular sightline, FRB 180924, and just tried to identify all the halos that could be intersecting along the sightline based on their photometric redshifts. And you get reasonable precision for this, I guess. This is dispersion measures in the halos alone, and it's a small fraction. So in this case, it didn't matter too much. But let's say if you wanted to build an IgM reconstruction, like I mentioned last week, this would be impossible. You would never be able to resolve individual filamentary structures because your photo-Z errors are so much larger than the length scale of these structures. So Definitely difficult to do. Maybe the approach that you would like to take is what Mariam Husseini and others took, where you basically look for overdensities in photo-Z catalogs and ask the question, is there any correlation between the excess dispersion measure along the site for this FRB sightline versus the galaxy number density in the field of view. So if you can't use photo-Zs, where do you go? Can I get free spectroscopic redshift still? The answer could be yes, especially if you have low enough redshift FRB hosts. So if you have low dispersion measure, chances are, especially this is true for burst, I'm sure, you already have redshift in some or the other catalog, and this is most likely going to be present in the in one of these two, 60F or 2MRS. So you're probably gonna get it for free. So of course the redshift coverage is not that high. You're looking at median redshifts of like at best 0.05, but that's still pretty good enough if all your hosts are going to be within, I don't know, 400 megaparsecs. You could go do slightly better with SDSS, and this is the main SDSS redshift catalog, where you can see the median redshift is much higher, and although it covers a smaller field of view, still you might get lucky, and we did get lucky in the case of 190608 and some other FRBs where we just got free redshift information for the hosts. Of course, DESI is going to be the next big thing in this space, and this will push the redshift window even higher. So the BGS sample is what you are likely going to be interested in, the Bright Galaxy Survey, and that has a median redshift of something like 0.25. So it doubles the redshift range available to SDSS, and it also covers a much larger field of view. So it could be that by the end of the DESI survey, you will have redshifts for a sizable fraction of your hosts. So this is basically a summary of what it's showing. There are multiple redshift surveys that are already available, some of them covering a large part of the sky, but shallow, some of them much deeper, but covering a smaller part of the sky. So always check these sources before you say, oh, I need spectroscopic redshifts. Of course, there are future surveys that are coming online. DESI, the complete DESI survey is going to be huge. There's also waves and foremost in the southern hemisphere, so it's not going to cover a large part of the sky, but nevertheless, anything is good to have, especially for experiments like Meerkat and Craft. And I guess Spotlight will also want a good number of southern host redshift, so something to look out for. Euclid and Roman are going to give you slitless spectroscopy, and that's kind of what it looks like. It's hard to see here, but each of these individual lines is a spectrum, a slitless spectrum, and this bright thing at the middle is the H alpha emission line. So by measuring the position of that emission line, you basically have a redshift. Of course, this is only good for redshifts greater than 1, but it's still going to cover a large part of the sky. So you have slitless spectroscopy that might yield you good results. What if you need your own spec-Zs? It's the same as imaging as before. So if it's just 2 to 3 order magnitudes fainter in terms of limits. So if you use a 4-meter class telescope, for instance, you could get decent spectra for objects brighter than 21st magnitude. And within an hour or so. 10-meter class, you could go deeper, and of course, like 6-meter, using JWST, you could go much, much deeper. But this is in infrared, so you have to worry about whether your emission lines will be in the wavelength coverage that you need. There are challenges, of course, in obtaining spectroscopic redshifts, even for the existing sample, as I mentioned previously. So this is a potential distribution of host magnitudes as computed by Lodrick Kahinga. And the idea was to start from FRB dispersion measures, convert that using the McCart relation to some sort of redshift estimate, and from there go towards look at the magnitude estimates of existing host galaxies and compute what the potential magnitude distribution would look like for Chime Catalog 1. That's what it looks like. So a lot of these FRBs will have faint hosts, order of like, beyond 23rd magnitude, where your imaging survey, you will require bespoke imaging many times, and also deep spectroscopy with 10-meter class telescopes at least. So DESI goes up to something like 21st magnitude. So a lot of these FRBs, you'll need spectroscopic redshifts yourself. And he also did a calculation of how many Chime FRB sources will be within the DESI survey footprint, as in we'll have spectroscopic redshifts, and it turns out something like 20% or so, not too high. So you still need spectroscopic follow-up for a large number of sources. Whenever we're writing optical proposals, it's a matter of convincing the time allocation committee and to telling them that, look, we're actually going to do some good science with these redshifts. And the question is always like, what will you gain from, I don't know, 10 more redshifts, right? And that's that's a practical problem, especially when you're dealing with the JWST TAC, where, like Kriti mentioned, so DSA is sitting on something like 10 hostless FRBs, which are super faint. But if you're just thinking about putting them on the McCart plot, the JWST TAC is going to ask you, what will that do, right? And so we need efficient science-oriented strategies for obtaining redshifts. We can't just say, oh, we need redshifts. Need to come up with better science cases. One potential solution to redshift conundrum is to just use large multiplexing instruments that have been already built. So DESI is one of them. Subaru PFS is yet another similar instrument, fiber-fed spectrograph. You can get something like 2,000 redshifts in a single pointing over 1.25 square degrees. And has an excellent wavelength coverage, so all the way from optical to IR. So you're going to get a lot of redshifts, a good redshift coverage with this. And because it's on an 8 to 10 meter class telescope, it's going to get, it can go pretty deep. That's what one of these sightlines look like. If you just have 4 hours on the PSF, and if you need redshifts for a fairly compact catalog of sources, then the PFS is your instrument of choice, and you can get something like 6,000 redshifts in one go, less than one night. So that is super impressive. Of course, the matter is with FRB hosts, you may not be able to densely populate this field of the PFS. So you might have to wait around a little bit, maybe collect a bunch of sources in a small field of view. And this might be the case for some, something like DSA 2000, where you'll have 10,000 FRBs a year. You just wait until you have enough FRB sources within a sightline, with let's say within 5 years or something, and follow it up with some multiplexing instrument like this. You could also do something like a targeted follow-up of subsamples. So of course, if you have 10 to the 4 FRBs every year, naturally, you're not going to be interested in every single one of these. You might be, you might only care about FRBs with specific properties. Let's say the host is unidentified, or it's super deep, or I don't know, maybe something like here in this case where this FRB has been localized to an elliptical galaxy, but at the FRB location itself, there's no bright source. So it could be a dwarf population, what have you. So you could be, you might want to just create subsamples to follow up. So here's another idea that you could use. So let's say you have a bunch of FRBs behind a cluster. You could use the dispersion measure to place constraints on the cluster profile. And then if you have a Z effect measurements there, then you could basically get temperature, pressure, and density constraints for the cluster gas right away. Okay, I'll try to finish it up. So yeah, you could also do something like an unbiased sample where you're just looking at a particular patch of the sky, let's say the poles, where you have a large sensitivity because you're just staring at it all the time, like Chime is. And you could follow it up with Subaru PFS because now you have a dense enough source set of targets there. Something that you might want to consider as a community is making all your redshifts public. DSA 2000 is going to do that. Maybe everyone else could also just supply their localizations for typical or boring FRBs, however you define that. And then maybe consider collaborations with teams that have multiplexing instruments, create an infrastructure to share FRBs and optical follow-up data. So yeah, that's basically things to think. Hopefully I've given you a lot of food for thought. So I'll leave my summary slides and happy to take questions now. Thank you for listening.
Yeah, questions for Sunil?
Hi, Sunil. Very nice talks. For cosmological survey, do we really need a spectroscopic redshifts? Because as you showed, the uncertainties are of the order of 3 to, let's say, like 5 to 10%. Whereas the DM uncertainties or scatter would be around 10%. Additionally, as you showed, like for catastrophic cases, I could use the DMDZ from IGM as a prior, and I can always remove the outlier.
Sorry, when you say DM from the IGM as a prior, like where are you getting the measurements from though?
Just from the mean density. The theoretical relation that you just get from the mean density of the universe. DM by DZ. So,
right,
don't put any observations on it, just draw a line. And then once you throw your observations to the photometric redshifts, okay, first of all, one redshift region I can easily remove if your low redshift sources are identified as high redshift sources. Those go below that, which cannot be possible. So you remove those as outlier.
Sure.
Additionally, I can come up with the priors based on simulations, based on only spectroscopic redshift, DM by DZ measurement once I have 10,000 of those, right? Sure. So using those, I think, I mean, like it's not a good idea over like after 5 years or 10 years down the line, when I have millions of sources from LSST being photometrically redshifted, right?
Sure. Yes, definitely true. It's just the point of the slide was to just make people aware that they have to worry about these biases essentially. Yes, maybe there are ways to use simulations to mitigate the effects that I've shown over here. Or like maybe LSST redshifts might be good enough for redshift 2 or even beyond. But so that's something to worry about. So over here, what gave me some pause was the fact that these are photos from Rubin, right? And you can see the coverage is not that great over here at high redshift, where cosmology for cosmological cases.
No, I don't know. One has to see the color bars. Okay, the color bars are basically showing most of the sources are at the center, one has to one line.
Sure. Yeah. It's the fraction is not too high. Like I said, it's something like 15 to 20% that you could get rid of. But you want to make sure that you're taking care of that. Is all.
Yeah, I think again it's very science focused.
Sure. Yeah.
Discussion.
Sure.
More questions for Sunil?
Very interesting, Sunil. So I have a questions like currently in the DSA era is mostly like we are going to probe the redshift region from 1 to 2, correct? That's where you have less and that is where getting populated. So how we're going to like what do you feel like how to kind of what kind of instruments will be actually suitable to handle those redshifts?
Yeah, I mean, it really depends on how bright the source is in optical, I guess. So if it's bright enough, then yeah, you could get away with just using Keck or some other 10-meter class telescope, say VLT or something else, and get your redshifts. But let's say it's not super bright in optical. So if it's going below 24th magnitude or something, then you have no choice but JWST essentially at that point. You could try MOSFire or some other IR instrument, but you'll have to get super lucky over there. The redshift has to lie between one of those I guess windows where the sky emission lines are not super strong. So you could make a decent enough measurement at the location. So I guess one thing to consider would be to pool up FRBs as a sample to build up a much more formidable sample to present to the TAC. So this might involve collaboration between FRB detection experiments, so DSA craft and I guess Meerkat, if they can come together and get all of their unseen FRB hosts together, so build a sample of 30 or something. Now we're talking statistically significant sample.
Yeah. Actually, my concern was mostly like when we see the upper bowl stock, like ratio 1.3, JWST is kind of struggling to get a emission from that point, detections. So we are trying to push beyond that. So
yeah,
already kind of seeing.
Yeah, I mean, at a certain point, you really can't do anything. You just hope that you could see, but there'll be a bias that you'll have to worry about. If you probably won't be able to associate hosts beyond a certain redshift range, or at least it'll be a luminosity cut, right? So you might only be biased towards the brightest galaxies as you go further and further in redshift. So you have to start worrying about the effects that would add to your analysis. Environmental effects, maybe.
In interest of time, we'll take the last question.
Yeah, so I was just wondering what fraction of secure for FRB host do we have the secure spectroscopic redshifts? And once you have the spectroscopic redshift, that would better constrain the host properties, right? Like for the projected host offsets or something like that. And in that case, if you cross match with the host properties of other transients, is there any similarities which you see in the case of offsets, let's say, or star formation rate or mass or something?
Right. So those are two questions. So the first one would be, I would say around 60 to 80% of our hosts have secure redshifts. The remaining 20 are either not seen or they're ambiguous, essentially. There's no path association to them, or like there's no definite path association to a single host galaxy. And then I guess to your second question, the analysis that has been done so far has been using a very small number of FRBs. So we probably need something of the order of 1,000 FRBs with arcsecond scale localizations, or even better, because you want to look at the exact location of the FRB within the host before you can say anything about comparing it against other transient distributions.
We have one question from online. Please go ahead, unmute yourself.
Yeah. So it's a very nice talk. So my question is about, so you didn't mention any of the stage 4 dark energy survey. So more specifically in the northern hemispheres, we have HSC and POW on the William Herschel telescope. In the southern hemisphere, we have dark energy camera and KIT. So is it that the magnitude depths are not deep enough to be interesting?
No, that's a very good point. HSC is certainly deep enough, and I think it goes down to 27th magnitude. It's just the fact that its sky coverage is low enough that we don't get a lot of hosts within those footprints. So yeah, that's pretty much it.
So, but what about the DS? I mean, that DS is, I think, pretty high. Is it that it's in the southern hemisphere and
DES is deep down to something like 24th magnitude.
Yeah.
So it's
Okay,
not.
so that's not
it's
deep
not as
enough.
deep as it's not as deep as HSC for sure.
Okay, then let us thank Sunil and move on to the next talk, which will be by Jahat. She will be talking about MRT study.